Greetings, physicists. This video will be about how to solve problems involving angular momentum and conservation of angular momentum. So, you got a little boy, I assume, standing on a merry-go-round, and he's going to walk from the center out to the edge. And we should be able to predict how fast the merry-go-round is going when he gets to the edge. So, let's write some things down. Alright, we got a mass. Oh, no, I don't want to do that. Here. We've got a mass. So, well, and let's draw it as well. This is always a good thing. So he's got merry-go-round. We have Joey somewhere right at the center. We got a distance. And he's going to travel all the way until he's at the edge. And it was spinning. So let's give it that. So he is 36 kilos. And for the purpose of this, we're going to actually represent him as a point particle because there's not a reasonable way to calculate his moment of inertia. At the center of a 200 kilogram merry-go-round. So the mass of the merry-go-round is 200 kilograms. That's there. We have that's an initial condition, right? It is rotating once every 2.5 seconds. And then he goes and moves to the edge. So we'll say that the omega initial is equal to once or 1 revolution per 2.5 seconds. And we can resolve that later. Radius is 2 meters. Cool. So, this can be considered a moment of inertia problem. And I'm going to do a before and an after. Because all the forces here are internal forces, he pushes on the merry-go-round pushes back on him, there's not going to be a net torque on this system. That would have to come from outside. So the total torque on this system should be 0. So any change in Joey's angular momentum has to be equal to the negative of the change in the merry-go-round's angular momentum. So we will expand that to say that it's delta, right? So I omega initial or final minus I omega initial for Joey has to equal I omega, and this is a negative, right? So that has to be I omega initial minus I omega final. And some things are going to make this easy. For instance, if we treat him as a point particle, then at the very beginning he is standing at radius 0. So he actually has a moment of inertia of 0 at the beginning, or 0 angular velocity, right? He's not technically, he's not going to have any angular momentum to begin with because he's at the center of the circle. So really, what we could say is that his I omega final for Joey has to equal the difference between the initial angular momentum of the merry-go-round and the final angular momentum of the merry-go-round. Now, some things that are going to be nice to calculate. The moments of inertia should be fairly easy, and there is no change in the moment of inertia of the disk. It's 200 kilograms, it's a uniform disk of 2 meter radius, and that isn't changing. So I can plug that in for the merry-go-round. If I'd like, I'll keep it down here that I is equal to mr squared. We can also say this, that when Joey gets to the edge, his final omega should be equal to the final omega of the merry-go-round, that those two should actually be the same. They will be rotating at the same speed. assuming that he doesn't have slipping. He's not sliding on the merry-go-round once he gets there. So let's see if we can put that together. I'm going to add this to the other side. So I should get this is the I of Joey times his final plus the I of the merry-go-round times its final should be equal to the initial of the merry-go-round. And that should kind of make sense. Really, the merry-go-round was the only one that started with angular momentum. He didn't start with any. So this is the total final angular momentum should be equal to the total initial angular momentum. Again, conservation of angular momentum statement. So let's plug some things in. And what we were looking for was omega final. So but actually, before I plug things in, let's solve for that. So I'm going to pop the omega final out. That would be omega final times I of Joey plus I of merry-go-round equal to, this is I of merry-go-round here, times the initial. And I'm going to divide by those. So we'll say final angular velocity should be equal to the initial moment of inertia, or the merry-go-round's moment of inertia times its initial angular velocity divided by the sum of the moments of inertia of Joey and the merry-go-round. All right, and now we can plug things in. The moment of inertia of a uniform disk is 1/2 mr squared. So what I'm going to do here is I'm going to say that this is all equal to, on top, for the disk is the merry-go-round, so 1/2 mass of merry-go-round times the radius of the merry-go-round squared times the initial angular velocity. And I'm dividing that by, well, a point particle, the moment of inertia of a point particle is just mr squared. So this will be the mass of Joey now times his radius squared. But his radius is actually the radius of the merry-go-round because he walks to the very edge. So he's also 2 meters away from the center. And so plus, on bottom, we're going to have, again, the moment of inertia of the merry-go-round, which is 1/2 times the mass of the merry-go-round times r squared. And look at that. There's an r squared term in all three. So for this particular problem, it simplifies in that we don't have to deal with the radius. That will make this calculation a lot easier. All right, so on top, what I'm left with is 1/2 mass of the merry-go-round. Oh, come on now. 1/2 the mass of the merry-go-round times its initial angular velocity over the mass of Joey plus 1/2 the mass of the merry-go-round. All right. And I think now we can actually plug some things in. The merry-go-round was 200 kilos. So if I half that, on top I'm going to get 100 kilograms times, and the initial angular velocity, I do know that. So on top, the initial angular velocity was 1 revolution per 2.5 seconds. And that's not in radians, so I'm going to change that to be 1 revolution is the same as 2 pi radians. I don't have to change seconds. Seconds is fine. That's a unit I like. On bottom, mass of Joey was 36 kilograms plus, again, 1/2 the mass of the merry-go-round was 100 kilograms. Well, let's do some simplification here. We have 2 pi divided by 2.5. So 2 pi divided by 2.5 gives me 2.51 on radians per second on top. So on top, I'm going to have this is 2.51 times 100, so I'm moving that decimal, so 251 kilogram radian per second on top over 136 kilograms. And look at that, kilograms will cancel. And I will get radians per second, which is an angular velocity, which is what I'm looking for. So whatever 251 over 136 is, 251 divided by 136. Okay. And I get 1.85 radians per second. Okay, now we got to be careful because yes, that is a final angular velocity, but I'm going to go back to the question. And look what it asks. What is the rotational period of the merry-go-round? So they actually want a time. Oh, that's tricky. Well, let's go back down here. So essentially what I have here is that this thing moves 1.85 radians in 1 second. We want a time. We want to get seconds for 1 revolution. We want to know how many seconds equals 1 revolution. So I'm going to try and change this into revolutions. So 1.5 radians happen in 1 second. So let's do some stoichiometry here. 1.85 radians times, well, 1 revolution, and I'm putting radians on bottom, is 2 pi. Excuse me, radians. So times 2 pi. No, excuse me, that's divided by 2 pi. All right, so what I'm getting then, it's per radian, is 0.2937, 0.2937 revolutions will equal 1 second. But I want 1 revolution, so we'll do the stoic here. 1 revolution times, we know, 0.2937 revolutions equals 1 second, and that should give me seconds. This is why you had to do so much stoic. Right, caret. And I get 3.4 seconds. So it takes 3.4 seconds for this thing to spin once after he gets to the edge. Whereas before he got to the edge, it rotated once every 2.5. So it went up by almost an entire second. And that should make some sense to us, right? If when he was in the center, he didn't have any moment of inertia. But when he was at the edge, he's going to have a much bigger moment of inertia. This is, of course, assuming he's a point particle. In real time, he did have a moment of inertia when he was at the center because his body has volume. But that would be increased with him moving to the edge anyhow. And so with a bigger moment of inertia, we have to have a smaller angular velocity by conservation of momentum. All right, good problem. On we go. All right, 2 boys now. So we have 2 people on a merry-go-round, or a turntable in this case. We know it has an angular velocity initial of omega I, and then they walk and they change their positions. What is the new angular velocity or angular speed? Good question. So let's think about this, because there aren't any numbers here. We have this guy here who's going to move to the center, and we have this guy here who's going to move to the edge. This is where they end up. And when I look at the initial bit, the important thing they tell me is they have equal mass, and they were each standing halfway between the edge and the center, right? If that's the radius, they were halfway, each of them. And let's look at how far they walked. This guy walked from here to here. He walked half a radius. This guy walked from here to the edge, which is also half a radius. So this guy took a mass and decreased its moment of inertia by that half a radius. And this guy took his mass and increased its moment of inertia by half a radius. So the net change in moment of inertia ought to be 0 if I'm doing that correctly. And we can probably do that mathematically because I just want to make sure. But their initial moment of inertia, I, would be equal to, if we're treating them as point particles, mr squared. And I would add them up. So the mr squared of boy 1 plus the mr squared of boy 2. And that should be equal to that they have the same mass, but they have the same radius, which was half of a radius. So we could say that m times half r squared plus m times half r squared, and half an r squared is a quarter. So if I add that all together, let's do this first. So this would be 1/4 mr squared plus 1/4 mr squared, or 1/2 mr squared. So this is their initial moment of inertia. When they move, the new boy, their final moment of inertia will be equal to their mr squared plus their mr squared. The new guy's r, he goes to the center, which is 0. He's at the center of the circle, so we're going to have a 0 for this r, so this guy goes away. Plus the new guy has twice the mr squared, so we'll say that he's up to regular old mr squared plus m times the full radius squared. I think I did that right. So if I'm doing that right, I should have a total final moment of inertia of mr squared, which is big. It's actually twice as big. Now, why does that happen? Let's figure that out. Well, why that happens is since they both have a certain moment of inertia at the beginning, they have an I, he has I initial, and he has the same I initial. They have the same because they're at the same radius. We're taking away his I. We're getting rid of one of those I's, which looks like it should halve it. That would be like halving the moment of inertia. But when this guy moves to the edge, since we're doubling his radius, and the radius is squared, when you double it, we increase it by a factor of 4. So removing his moment of inertia takes away half the original moment of inertia, but doubling his radius, 2r squared, quadruples his moment of inertia. So we actually get a bigger effect by that double than we get by taking his away. What an interesting turn of events. So if it was rotating with initial speed omega, what is the final angular speed? Well, we have a bigger moment of inertia, so we have to have a smaller angular speed. So it should be less than omega initial. That's a tricky one to do, especially if you were trying to do it fast. All right, last one. Here's some numbers. This is just a straight-up angular momentum calculation. What is the angular momentum of the moon around the Earth? They give the mass of the moon, and they give its distance from the Earth. They don't give the radius of the moon. So when we draw this system, let's draw the Earth here, and the moon out here, and it's going to go around the Earth like that in a circle. I think we have to assume the moon is a point particle. Otherwise, they would have given us its dimensions, which would kind of change this a little bit. Alright, so what is the angular momentum of the moon? Alright, well, the angular momentum of the moon, L, should be equal to its moment of inertia times its angular velocity. What's given to us? Mass and radius. Well, that helps with this. So what we can do then is say that the angular momentum of the moon should be equal to the moon's mass, the mass of the moon, times its orbital radius, r squared, times its omega. Well, these are given. Now, so the tricky part of this problem is how long does it take, or how fast is the moon moving. And if you were going to do it the second way I said, how fast is the moon moving? You could try to look it up, I guess, but on a test it might not be given to you. But you do know, you probably know, that the moon goes around the Earth in 28 days. So you could say that 28 days is equal to 1 revolution. So the angular velocity of the moon is equal to 1 revolution per 28 days. So that's kind of relying on you to have that number memorized. But if you do, you can plug these things in. So let's plug in what they gave us. Well, I forgot what the mass of the moon was. 7.4 10 to the 22nd. All right. So the angular momentum for the moon is its mass, 7.4 10 to the 22nd kilos, times its radius. I happen to know the radius because it's the same as the speed of light. Its orbital radius, 3 times 10 to the 8th meters, but I'm squaring that. So squared, and its omega is 1 revolution per 28 days. Now, I really am going to have to convert that. So it's going to be times, let's get rid of rev, 1 rev per 2 pi radians. And I'll have to do days to seconds. So let's give ourselves some room before we do that. Or I can just slide over here, I suppose. Radians times 1 day per, I guess it's 24 hours times 3,600 seconds in an hour, so 24 times 3,600 seconds. Okay. That's a lot to put in the calculator. Again, I don't recommend putting tens in your calculator, so I have a squared 10 to the 8th, so it's a 10 to the 16th, and I have 22 tens here. So I'm just going to say that whatever answer I get, I'm multiplying by 22 and 16, so 38. So there will be 38 of these left over. And then let's do the rest in the calculators. The rest, 7.4 times 3 times 2 pi on top. The rest are all ones. On bottom, it's going to be 28 times 24 times 3,600. And you can do some canceling if you like. 2 times 3 on top is 6. 6 over 36 is 1 over 6, so that's like 600 on bottom. You could actually take 2 tens off of that and make this a 36. Okay, so it's going to be 6 times 24 times 28 on bottom. I don't think there's much more to cancel here. All right, calculator, try it here. 7.4 on top times pi divided by 28 divided by 24 divided by 6. Okay, and I'm getting 0.00576. That's going to round up to 577 actually, times 10 to the 36. So let's move that decimal 1, 2, 3. So 5.75, 0.77. I'm sorry, I needed to round that. 5.77. That's losing 3 tens, so I have to go down to 10 to the 33rd. Okay. And that should be in the right units, radians and seconds and all of that. So if I really want the right units here, remember what I had. I had I omega, which is mr squared. Omega, which is kilograms, meters squared per second. You can put radians in, but a radian is sort of a unitless thing. So 5.77 10 to the 33rd kilogram meter squared per second. Lots of angular momentum, largely because of the mass is so big and the distance is so big. Those are the big contributing factors. Okay, so those are 3 angular momentum problems. Hopefully this helps you in your attempts to solve angular momentum.